Okay, hello everyone, this is Dr. Galstein. This will be the third lecture on the topic of optimization. In the past two lectures, I explained kind of what optimization is and how we do it in principle. And then I also gave a bunch of examples and also demonstrated what it looks like to optimize a function subject to a constraint. Now I want to add a little bit more depth to our work with optimization. I want to look at a couple of different topics in this lecture, and this will be a relatively brief one, I think. I want to talk about comparative statics. I'm awful at spelling, sorry. Comparative statics, or interpretation. Basically, I want to kind of have a little bit of a discussion of, what some of this optimization means. I want to then introduce something called the indirect objective function. The indirect objective function, or sometimes what we will call the value function. All right, what that is. And then I want to introduce the envelope theorem. All right, so that's the goal for this little lecture. So let's go ahead and jump right to it. I think that to get into this lecture, we need to I'm going to very quickly solve a constraint optimization problem. I'm going to very quickly do it. It'll be by way of review, but also to give us a little bit of something to work with. All right. So let's say that we want to let's see. There we go. We want to find the value of x and y that maximize some function natural log of x and y. Subject to some constraint, and it's just going to be this generic one. We solved this exact same problem in the last lecture, so I'm just going to go very quickly through it. Okay, so let's say we want to do this. What we do, as you know, we set up the Lagrangian. Okay, natural log, we break apart that natural log. All right, have our constraint in there. Y, okay. We do all of our first order conditions. All right. So I've already done this exact same thing. This is review. So I'm just going to go through it quite quickly here. Set it equals 0, first order condition. Set it equal to 0. Z minus alpha x minus beta y. All right, we got to solve all of these for x, y, and lambda, so let's do that. All right, so if we solve this, we'll get x equals 1 over lambda alpha, y equals 1 over lambda beta. So we plug these two things in down here, and we will get z minus 2 lambda equals 0. So we solve that and we get lambda equals 2 over z. We take that, plug it back in up here, and what we will get is that x star, so let's do lambda star here, x star equals z over 2 alpha, y star will equal z over 2 beta. All right, so there we have it. Just quick review, very quickly solving these things out, not really showing my steps, but I'm going to use this as an illustration, okay? So this is where we left off in the last lecture, so I'm just going to erase everything else here. I'm going to put those solutions up in the corner, and we're going to move from there. So it's basically picking up where we left off in the last lecture. All right. So I'm just going to write them up here. X star is equal to z over 2 alpha. Y star is equal to z over 2 beta, and lambda star is equal to 2 over z. Okay, so let's erase this, and let's discuss some interpretation. Let's try to get some intuition here. Okay, so what we have here is we have functions. Now, this variable, we had variables x, y, and lambda. These were all variables at the beginning, but now we have each of them as a function. So these variables have become functions. These variables are functions of the parameters. Okay, y is a function of the parameters. Lambda is a function of the parameters. Okay, so now we have functions of the parameters. We have these as functions of the parameters. Well, now we might find ourselves in a situation, and we certainly will once we get into kind of the full economic expression of these topics, but we might find ourselves in a situation in which we want to know how changes in the parameters would affect x or y or lambda. So we might want to know how a change in a parameter would affect a variable. We might want to know that. This will make even more sense when we get into the economics. But suffice it to say for right now that we might want to know how maybe x changes when alpha goes up or when z goes up. Well, how would we do that? We might want to know that. How would we do that? Well, we would take the derivative. So let's say I wanted to know what is the change of x star given a change in z? Well, I would take the derivative. So what's the derivative of x star with respect to z? Well, that would be 1 over 2 alpha. What if I wanted to know how x changes given a change in alpha? Well, I'd take the derivative of x with respect to alpha. Now you'll notice here this kind of requires a chain rule, the quotient rule, but we might make it easier, just bring that denominator up. Let's do it over here. Z times 2 alpha to the negative 1. Let's take the derivative. Negative 1 z 2 alpha negative 2. And so what we'll get is we'll get z over 2 alpha squared. Okay. All right, so these expressions tell us how the parameters will affect the variables. That means how the optimal decision, how the optimal x is affected by a change in one of the parameters. So basically, if z increases, then x star, the optimal x, increases by 1 over 2 alpha. This is positive, so it increases. If alpha increases, then x star decreases by z over, I can simplify this, 4 alpha squared. All right, so this basically gives us an interpretation. It allows us to start to use this math in a way that can maybe potentially tell us an interesting story. All right, so if I wanted to know how does a change in z affect the optimal x, well, if z increases, x will increase by 1 over 2 alpha. All right, so we can interpret this. We can tell a story. We can say that as z goes up, so as z goes up, x will go up, or x star, I should say. We can say that as alpha goes up, x star will go down. We can tell a story about the way that these parameters will affect these variables. All right, that might not sound very interesting right now, But if we're astute and we kind of look ahead to what we'll be doing in the future, imagine that we've done a constrained optimization where the variables are choices, like how many cups of coffee to consume and how many hours to spend studying. And then the parameters are things like people's income or the amount of time that they have. In that case, we might really want to know how changes in the parameters will affect the optimal decision that people make. More on that later. All right, but this gives us an idea as to how we can use some of this math to tell a story. All right, and so that lays that foundation. Okay, let's do a little bit more interpretation. Now we noticed, we noticed that when we did this Lagrange method to solve a constrained optimization problem, we introduced a variable that we didn't explain. I didn't talk about it. I did not talk about what this lambda is. So let me rewrite this Lagrangian and we'll talk about it. All right, let's rewrite the Lagrangian. It's a function of x, y, and lambda. Okay, and it's the natural log of x, y plus lambda with the constraints. Okay. All right. I never talked about what this lambda is. And so let's take a second to just talk about what this lambda is. Let's get some intuition on it because it's actually quite interesting. And when we get into the economics, it's going to become even more interesting. But what this lambda is we would call this lambda, first let's give it a name, the Lagrangian multiplier. Okay, the Lagrangian multiplier. All right. It's a helpful parameter that helps us to solve the maximization problem. So just from a mathematical standpoint, it's a helpful variable. We add it in and it helps us to solve for the maximization. But it actually has a meaning. It has a meaning that we will discuss more later when we get into more of the economics. The Lagrange multiplier is the marginal cost of the constraint. It's the marginal cost of the constraint. Sometimes we'll also call it a shadow price. Okay. We're going to go into that more detail once we get into the economics, and we'll be able to flesh that out a little bit more. Okay, so those are two quick things by way of interpretation. All right. Now, let's take a look at what we call the indirect objective function. Now, all right, I'm going to come back up here, and we're going to write this again. So our Lagrangian function, x, y, lambda equals ln x, y plus lambda z minus alpha x minus beta y. Okay. Now, this was our function, and we went through the complicated process of finding the optimal values, the values that maximize this function. All right, that's x star, y star, and lambda star. Now, what if we took these values and we plugged them back in? If we plug these values back in, we would get a new function, so x star, y star, lambda star equals natural log of x star, y star, plus lambda star, z minus alpha x star, minus beta y star. All right, this function here, we call this the indirect objective function. The indirect objective function. Okay, this function, this indirect objective function, once we've plugged all the optimal values, once we've plugged all of the optimal values back in, this is the optimal level of L. This is the optimal level of L. This is the, in this case, because we're doing a maximization, this is the maximum that L can take. Another way of putting it, this is the max value of L. The max value of L, remember L is composed of the original objective function. The original objective function is the natural log of that, all right, plus the constraint, okay? So the max of L is basically telling me it is the constrained maximum. Okay. Now, so we've got all that. So this is the indirect objective function. Sometimes we will also call this the value function. Basically what we've done is we've taken our optimal values of x, y, and lambda, and we've plugged them back into the function, and now we have the indirect objective function. It is the function at its maximum. That's if we're maximizing. It also could be the minimum if we were minimizing. Okay. All right. So with that said, what can we do? Well, what can we do with it from there? Well, let's make a couple observations. All right, I'm going to erase this now. All right, this function, this optimized function, has it's somewhat interesting in a couple ways. First, one thing we will notice is that x star, y star, and lambda star are all functions only of parameters. All right, they're functions only of parameters. That means this function is a function only of parameters. I could write it this way. Z alpha beta y star z alpha beta lambda star lambda star z alpha beta. All right, it is a function only of the parameters. That means I could plug x star in, y star in, and lambda star in. I could plug them into this equation, and it wouldn't have any x's, any y's, and any lambdas anymore. It would be entirely composed of parameters. Let me do that real quick. I'll show you what I'm talking about. All right, so I'm going to take this, and I'm going to plug x star, y star, and lambda star in. So we get natural log of z times 2 alpha times z over 2 beta plus lambda star is 2 divided by z, all right, multiplied by the constraint, z over 2 alpha minus beta, z over 2 beta. All right, so here is the Lagrange, the indirect objective function, so the Lagrange function with the optimal values plugged in, and so here we have it. Okay, when you look at it, there's no x's, no x, no y, and no lambda anymore. Only parameters. Only parameters, z, alpha, beta, and then of course the numbers like 2. Okay, so once we've optimized and we've plugged back in, now we have a function that's composed entirely of parameters. There's no more variables. Okay, what this means is that basically if we know all of the parameters of the model, we will be able to calculate the maximum level of constrained utility. If this was a utility function, the maximum level of the constrained objective function, right? We would find the maximum level of the Lagrange function, all right? If we had all of the parameters. Okay, now with that said, we might, just like we had before, remember just a moment ago I showed that we might be interested in knowing what is the derivative of x with respect to a parameter like z. Right? How does an increase in the parameter z affect x star? Remember, and we said that that derivative is 1 over 2 alpha. It's positive. Okay, great. We might want to know, how does a change in the parameter, how does a change in the parameter z affect L star, that optimum level? How does it affect that optimal level? We might want to know this. How would we calculate this? All right, well, let's do some erasing and then let's figure it out. All right, I'm going to show you a trick here. Okay, we're going to get into something that we call the envelope theorem. All right, let me erase a little bit here, give us some space. All right, so we want to know, how does a parameter affect L? All right, so here's our function L. It is a function of x star, y star, and lambda star, okay? And we want to know, how does an increase in z affect L? And we might say L star for shorthand. We might say L star for shorthand. All right, how does an increase in z affect L star? All right, that means we want to know the derivative of L with respect to z. All right, now if you remember when we talked about total derivatives, now total derivatives are going to come into play here. Now total derivatives are going to come into effect. Let's see how. First, we need to observe that this L is a function. All right, it's a function of x, which is a function of z. It's a function of y, which is a function of z. It's a function of lambda, which is a function of z. And it directly has the parameter z in it. So now we're going to take the derivative of L with respect to z. How do we do that? We take the total derivative. Okay, we take the total derivative. So let's do that. It's the derivative of L with respect to x. So use a chain rule, right? Derivative of x with respect to z, plus the derivative of L with respect to y times the derivative of y with respect to z, plus the derivative of L with respect to lambda times the derivative of lambda with respect to z, plus the derivative of L with respect to z directly. Now, if you remember from class, these are all partial derivatives. This is the direct derivative. This is the direct derivative. All right, so here, if we want to know how does an increase in z affect L? Well, here is your answer. How does an increase in z affect L? Well, this is it. It's this big monster. All right. Now, a moment ago, I actually showed you what it looks like to plug these functions into L. It's quite messy, right? Well, we're actually able to use a trick. All right, we're actually going to be able to use a trick that would simplify this calculation. All right, so let me show you what it is. I'm going to erase this. Okay, and actually I need to add one thing to make sure we're clear here. This is x star. This is y star. This is lambda star. Okay. All right, so now we need to look very carefully here, and we will be able to find a trick that makes this calculation much easier. Okay, what could that trick be? What could that trick be? Well, let me remind you that at the maximum, at the max of a function, the derivative of that function at the maximum point equals 0. The derivative of the function, say some function f, the derivative of that function with respect to x equals 0 at the optimal point. right? This is the truth. This is that first order condition, right? We solved this. We did this. We know that this is true. This is nothing new. Well, based on this information, okay, we can make a very important observation here. Let's make a very important observation. X star is the optimal value of x, y star is the optimal value of y, lambda star is the optimal value of lambda. Okay, so then the derivative of L, the function, the derivative of L with respect to x at x star is equal to 0. The derivative of L with respect to y at y star is equal to 0. The derivative of L at lambda, the derivative of L with respect to lambda at lambda star is equal to 0. That means that all of the partial derivatives equal to 0. That means if we want to know the derivative of L with respect to z, we only need to calculate the direct derivative. We only need the direct derivative. Okay, so if I wanted to calculate how does an increase in z affect L star? I only need to calculate the direct derivative. I'm going to do that up here. Sorry for not using my space well here. So if I want to know how does a change in z affect L, well, I take just the direct derivative. Basically what I do is I ignore the fact that x, y, and lambda are all functions of the parameters. I ignore that, and I just take the direct derivative. The direct derivative, if you look at this, with respect to z, is lambda. This is the direct derivative. It's actually quite simple. So even though we have some big monster equation here, all of this drops out, equals 0. It's just the direct derivative, and here it is, no problem. Very quickly. All right, now I'll get rid of those stars. It is important, but the stars will be confusing. Okay, so here we go. Now, I'm going to erase all of this, and I'm going to summarize what I just showed you, and I'm going to give it a name. Envelope theorem. Okay, so here we go. So if we optimize a function, so let's say we optimize a function. So if we optimize a function, so let's say we have this Lagrange function, okay, we optimize it. That means that we find x star, y star, lambda star. That means these are the values at which this function reaches an optimal, okay? We take them and we plug them back in, we will get this indirect utility function, or indirect objective function. All right, so it's basically the objective function at its optimal. All right, and then, all right, and also remember, x star, all of these are functions of the parameters. Okay, functions of the parameters. All right, and then if we wanted to know the impact of a change in a parameter, we'll just say z, then that is equal to just the direct derivative. It's equal to just the direct derivative. You don't have to differentiate. You don't have to do the chain rule for all of the separate components. All right, this is called the envelope theorem. It will be very useful. It will be one of your best friends in this class. All right, we'll reinforce it later once we have to apply it. I just want to give you that heads up. All right, so here we go. This is the last lecture on optimization. I hope you found it interesting and informative. Let me know if you have any questions, and I hope you have a great day.